With AI, capable to solve all sorts of lead code problems, should we still be learning about algorithms and data structures? What's the point of learning complex algorithms when you can just tell the AI to give you the finished implementation? Welcome to Frankly Developing. I'm your host Frank, and I have learned about algorithms a lot. So much, in fact, that I participated in algorithm competitions on the world-class level, essentially doing what an AI can easily do nowadays. So, would I recommend to developers that they should learn about algorithms? Keep watching to find out why my answer is yes, but no, but yes. First of all, the answer to whether you should learn about algorithms and data structures can be very simple. If you enjoy it, if you like wrapping your head around these things, and have a good time learning it, applying it, implementing your own algorithm variations, and that sounds exciting for you, then sure, go ahead. Don't let me stop you. Like anything in life, learning something new is a value in and of itself. You may want to learn how to weave a basket, or how to write with a bird's feather, or how to build a trebuchet. If you enjoy it, you probably don't even need to ask the question. Just go for it. On the other hand, once someone considers learning algorithms, it's probably more because they think it might be beneficial for their career, helps them to become a better developer. For that decision, you should first check if you want to become a better developer. Some people claim that AI will replace us. Though personally, I don't think so. Check out my other video if you want to know more about this. Let's assume you think there's a future for you as a developer. What role will algorithms knowledge play in that future? If you want to get into one of the huge FAANG companies, they still require that knowledge in the interview process. So if that's your goal, there's no way around it. If you want to join any other company on the planet though, it's already quite different. As a professional developer with a strong background in algorithms, how often do you think I'm using that knowledge? How often do you think I will implement an algorithm? Well, the answer to these two questions is quite different. I'm barely implementing what I would refer to as an algorithm. Maybe once every sprint or so, I find some application for a pretty common algorithm, like a BFS, DFS, or some recursive visitor. The rarer ones though, well, those come up just a few times over the course of an entire project. Do you know that there are two classes of algorithms? The upper class algorithm that has been named by a person, and the lower class algorithm named just by that technique usually. So examples of upper class algorithms would be the famous algorithms invented by Dijkstra, Knuth, Morrison-Pratt, Aho and Karasik, and so on. There are a few exceptions here and there, of course, but it's interesting to look at the real-world usage of these. The upper-class algorithms aren't something you just come up with by doing a bit of hard thinking, unless you're a genius. So they are harder to understand, harder also to implement, and particularly error-prone if you just get the tiniest detail wrong. Also, they are very specialized, so they cannot be used everywhere. But they are the best of class for a tiny set of problems. I practice implementing these for years when doing competitions. And you need to do so as well if you want to go into competitive programming. But what if you don't want to? What if you just want to work as a developer? How often do I implement one of these upper class algorithms? I can tell you the precise number: 0. Nada. Because you should not do that. These algorithms are tricky to get right, need a lot of time investment to develop. And why would any financially interested organization do that when you have battle-proven open source libraries available that can do it for you? So that's part of an answer for you. Should you learn to implement these algorithms? Definitely not needed. Learn it if you love it, sure. Ignore the implementation details and you'll be just fine as well. Is it cool that AIs can implement such algorithms? Yeah, absolutely. Would I ever use such an implementation in my projects? No, never. Just as I wouldn't want one written by an expert either. let's do a small demo here with Cursor AI. Let's say we want to do a small game with a map that is two-dimensional. I have a grid, and that gives some pretty typical algorithms here. And it'll give us like a game, which has a map class, which is a width and a height, and the unit is a class here with some unit symbol. You can initialize units. You have a main loop that runs and draws the map and moves the unit. So let's just take that and run it. I can enter the unit to move, a direction, and it'll update. So I have two A units. The output here, so the output overlaps kind with the other one. Maybe open this a bit more. That looks better now. So I can actually play it already. Pretty amazing already. Alright, next we want to, of course, look into algorithms. So what about if I want to find the shortest path between 2 points? Okay, and then it will implement the A or A star algorithm. Oh, A star probably. Does some changes. Moves units to a target. We can specify target X and Y apparently. Looks for the path, draws it, and so on. Sounds good. Let's give it a try. Lots of code actually here. Wow, so much code. I see there are some things involved like computing neighbors and some heuristic cost stuff. Okay. Some Manhattan distance. So, well, you better know what that means, or it's kind of like no idea what this is doing at all. So yeah, we replace it, we run the program. Let's make it a bit larger again in case it's an interactive one again. Ooh, lots of warnings. Okay, so can move a unit to the target. Again, let's move A to, I don't know, 7, 9. And you see it moves there, well, just over the B, but that's fine. We didn't specify anything like that yet. Okay. Oh, we don't have an exit. Let's take a look at the code. Move unit to target. There's a find path method. And the find path method, which is a list and hash set and open set count, it's doing an ordering each time in the first one. That doesn't look very optimized yet. It's kind of strange implementation for an A star to have a loop and do an ordering each time in the loop. That's the neighborhood, and eventually, there we go. We have the heuristic cost, and it's not the cost it's ordering by, really. G cost, H cost, F cost. There's 3 different costs. So there's the heuristic, indeed, a Manhattan distance. Path reconstruction, sure enough. And F cost, okay, alright. It includes the heuristics and the tentative costs. All good. Right, that'll work. It's a bit of a old style of programming, but as usual, LLMs are a bit behind on their learning. Not always using the latest version of a language, of course. Cool. Okay. Now, let's make it a bit more interesting. All right, let's add something like mountains. Okay, and you see that it's already starting to make a few strange decisions, like in the map class. It's adding a separate mountains to the Boolean array, so we don't have a representation of the maps. Instead, we have like a Boolean array where the mountains are, and probably wouldn't design it like that. But it's okay, we can work with it. Let's take a look at how it looks like now. Even more warnings. Oh, cool. Here we go. Let's say I want to move to unit A, 248, and you see it walking nicely around the mountain. Oops, no, wanted to exit. Works just fine. Cool. Okay. Now, what if I think this is just so? Let's ask it to make it fast. Okay, and there you go. It's like, this is the gist of it. To speed it up, the main bottleneck is this list implementation for this open set and finding this lowest cost node. And it's optimized using a priority queue, which would be your first go-to if you go for an A-star implementation usually. And there's the foreclosed set, yeah, alright. So there we go, that's a priority queue. And again, it's like basic knowledge. What priority queues do is like they keep this thing in sorted order so you don't have to resort it each time. Other than that, it should be pretty much the same. And we can also just ask the AI how to make it even faster. And here you see that a few things come up, like the jump point search, a bidirectional search, we search from start and goal side, hierarchical pathfinding, where we divide the map into sectors if you have a really large one, path smoothing to avoid zigzag, and then it already suggests to implement the the jump point search. It's getting a lot more code. I see it like this is working just fine, and it's implementing the algorithm. We have over 300 lines of code already for a working algorithm for a base simple game in place already. Well, let's stay on a higher level then, and you might ask yourself, do you need to know the high society of algorithms? Do you need to know which upper class algorithms exist and what niche problem they solve? Again, I would argue no. Knowledge is becoming a commodity. Just ask the AI. You saw it come up in this demo with the A-star, with the jump point search, etc. All of these things are knowledge you do not provide or have to provide yourself anymore. You explain your niche problem and it'll give you the names of these algorithms. So there's no need really for you to go through learning all of these anymore. So finally, why am I falling back in the end to still say yes, you should learn about algorithms and data structures? Well, with AI being perfectly capable of writing the implementations for you, and it also knowing all of the algorithms, why would you still need to care? Because if you don't understand what the program is doing anymore, then it'll be really hard to judge the impact of changes. There's some basic knowledge around these things that is absolutely crucial for all our design and architectural decisions and considerations. That's the sort of understanding we still need to make good judgment calls. You want to know enough about the algorithms you're using to understand the specific problem they solve, so that you know when the requirements change that problem. You want to know the underlying assumptions, as the algorithm guarantees are gone if you start violating them. You want to know time and memory complexities and recognize when you are in a setting where these may become problematic for your usage. And yes, AI may help you with that. That's the interesting thing. It kind of all knows all of this. At this point though, you also need to know and at least ask the AI about it, and then to double check your requirements and needs. Maybe AI will become more proactive in the future and try to elicitate this information from us. Even then, it depends very much on how it asks. Without this basic knowledge, could you even answer for our demo example if the A-star performance is sufficient, given that its runtime is exponential with the branching factor and the depth of the shortest path? There's no easy way to tell how all of this will advance in the future, but it's already clear now that developers will not learn about algorithms like we did in the past. If you want to develop your own algorithms one day, sure, there's no way around the hard work of digging deep into this world. For most developers and projects, though, this is needed. You also don't need to be able to correctly implement these algorithms. You don't even need to be able to name them or know of their existence. But if you consider data structures and algorithms as the basic building blocks we work with, you want to know about their properties, understand enough about them to use them in the right way, and know where the limitations are. Let me know in the comments how you approach this topic, and if AI has already changed how you think about algorithms. Thank you very much for watching and have fun developing.